14 billion years. That is how long this universe has been running. 14 billion years of stars burning, galaxies forming, planets cooling, chemistry doing its thing. And in all that time, across all that space, with all those chances, nobody has shown up. Not one knock on the door, not one signal, not a single fingerprint left on the glass. Now that is a crime scene worth investigating. Let me set this up for you properly because the numbers matter. Our galaxy alone, just this one spiral of stars we live in, contains something like 200 billion stars, maybe more, and current estimates put the number of galaxies in the observable universe at roughly 2 trillion. So you are dealing with numbers so large your brain honestly cannot picture them. Nobody's brain can. These are numbers that only make sense on paper. And here is what makes the silence worse. Our sun is not special. It is a perfectly average, middle-aged, yellow dwarf star. Nothing remarkable about it. There are billions of stars older than ours, stars that formed 5, 6, even 8 billion years before ours did. Planets around those stars had a head start on us. A very big head start. If life arose on any of those planets, and if it followed anything like the trajectory it followed here, those civilizations should be millions or even billions of years ahead of us. So where is everybody? That question, phrased exactly that way, supposedly came up over lunch in 1950 at Los Alamos. A group of physicists were chatting about flying saucers of all things, and Enrico Fermi just blurted it out. Where is everybody? And the table went quiet, because when you actually sit down and think about the numbers, the silence is not just surprising, it is disturbing. Statistically, you would expect civilizations to be everywhere, not one or two, thousands, maybe millions, and yet the sky is quiet, the evidence drawer is completely empty. So let us work this case, one clue at a time. Round throwers. The first thing a good detective does is check the basics. But could civilizations exist out there? Well, we know the chemistry works. Carbon, hydrogen, oxygen, nitrogen, these are among the most abundant elements in the cosmos. They are everywhere. Water is everywhere. Organic molecules, the building blocks of the kind of chemistry we call life, show up in interstellar dust clouds, in comets, in meteorites that have been drifting through space for billions of years. The raw ingredients are not the bottleneck, the universe is practically soaking in them. And we know planets are common, enormously common. Since the mid-1990s, we have confirmed thousands of planets orbiting other stars. Some of them sit in what we call the habitable zone, that comfortable orbital distance, where temperatures allow liquid water to exist on the surface. Conservative estimates suggest there may be something like 40 billion Earth-sized planets in habitable zones, just within our own galaxy. 40 billion. That is not a small number. That is 40 billion separate chances for something interesting to happen. So the materials are there, the locations are there, the time is more than sufficient. What is missing? Well, maybe the problem is not getting life started. Maybe the problem is getting from bacteria to a civilization that can cross the space between stars. And this is where the physics starts telling us something deeply uncomfortable. Let us talk about distance first, because people underestimate how big space really is. The nearest star to our sun is Proxima Centauri. It is a little over 4 light years away. That means light, traveling at 186,000 miles per second, the absolute speed limit of the universe, takes more than 4 years to get there. In miles, that is roughly 25 trillion. 25 followed by 12 zeros. If you drove a car at highway speed, it would take you about 50 million years to arrive. The distances involved are not just large, they are obscene. And that 4 light-year gap is the shortest one. Most of the galaxy is much farther away. The galaxy itself is about 100,000 light-years across. Interesting target stars with promising planets might be tens, hundreds, or thousands of light-years from any given starting point. Now, physics puts a hard ceiling on how fast you can travel. Nothing with mass can reach the speed of light. Period. That is not an engineering limitation. That is a law of nature built into the structure of space-time itself. As you push an object faster and faster, the energy required to accelerate it increases without bound. Getting to 99% of light speed would require more energy than you can practically imagine. So let us be generous. Suppose a civilization builds a ship that can travel at 10% of the speed of light. That is already extraordinary. That is 18,600 miles per second. At that speed, reaching Proxima Centauri takes about 40 years. Reaching a star 100 light years away takes 1,000 years. Crossing the galaxy takes 1,000,000 years. But even 10% of light speed demands a monstrous amount of energy. Then you can calculate it. The kinetic energy of a modest spacecraft, say something with the mass of a large truck traveling at 10% of light speed, comes out to roughly the energy a small country uses in an entire year. And that is just the kinetic energy of the payload. The actual fuel required is far greater because you have to carry the fuel with you, and the fuel to carry the fuel, and so on. Rocket physics is cruel that way. The fuel problem grows exponentially. This is what engineers sometimes call the tyranny of the rocket equation. Every kilogram of fuel you add requires more fuel to lift that kilogram, which requires more fuel to lift that fuel, and you end up needing absurd quantities of propellant for even modest speeds. So right away, physics is putting an enormous price tag on interstellar travel. Not necessarily an impossible one, but a price tag that requires a civilization to command energy at a scale we can barely fathom. Now here is where a less careful detective would stop and say, well, maybe they just need more time to develop the technology. Fair enough. Let us grant that. Let us suppose a civilization survives long enough, gets clever enough, and starts seriously working toward interstellar capability. What does physics predict happens next? This is where the case takes its dark turn. There is a pattern buried in the physics, and once you see it, you cannot unsee it. Every technology that gives a civilization the power to reach the stars also gives that civilization the power to destroy itself. And this is not a coincidence. It is a consequence of how energy works at a fundamental level. Think about nuclear physics. The same understanding of the atomic nucleus that could, in principle, power a starship. That same understanding also produces weapons capable of ending a civilization in a single afternoon. Fission and fusion do not care what you point them at. The energy is the energy, the knowledge is the knowledge. You cannot learn how to build a fusion reactor for propulsion without also learning how to build a fusion bomb. The physics does not allow you to separate those two things. But they come from the same equations, they emerge from the same insights about how nuclei bind together and how much energy is released when you rearrange them. And it goes beyond nuclear technology. Consider what it really takes to harness energy at the scale needed for interstellar flight. You need to manipulate matter at a fundamental level. You need to control reactions that release enormous amounts of energy per unit mass, whether that is nuclear fusion, antimatter annihilation, or something even more exotic we have not yet imagined. The principle is the same. Any civilization wielding that kind of power has, as an unavoidable side effect, built the capacity to render its own planet uninhabitable, not through malice, not necessarily through stupidity, through the simple reality that the more powerful your tools become, the smaller your margin of error gets. Let me make this concrete. A spacecraft powered by matter-antimatter annihilation, which is one of the more plausible ideas for getting to a reasonable fraction of light speed, would carry fuel with an energy density millions of times greater than anything in our current arsenals. A malfunction, a miscalculation, a conflict over who controls such a drive, any of these could release energy equivalent to thousands of nuclear weapons in a single event, and there is no version of the physics where one outcome is possible and the other is not. The engine and the bomb are the same object pointed in different directions. But wait, let me show you another angle on this problem, because the danger is not only about weapons. There is a quieter trap, and it comes straight from thermodynamics. Any civilization that uses energy produces waste heat. This is not optional. It is not a design flaw you can engineer around. It is the second law of thermodynamics, one of the most ironclad statements in all of physics. You cannot convert energy from one form to another with perfect efficiency. Some fraction always degrades into disordered thermal energy. Always. No exceptions. No cleverness defeats this. It is written into the fabric of reality as deeply as anything we know. A civilization advanced enough to contemplate star travel would be consuming energy at a rate that fundamentally transforms its own environment. We can already see the faint beginnings of this effect on our own planet, and we are using energy at a level that is laughably primitive compared to what interstellar travel would require. Scale our energy use up by factors of 100 or 1,000, which is what you would need for serious interstellar capability, and you have a civilization that is literally cooking its own biosphere, not through carelessness or negligence, through physics. And here is what makes the thermodynamic trap truly vicious. That it gets worse the more capable you become. Higher efficiency means you are processing more total energy, which means more total waste heat, even if each individual process is cleaner. You can improve the ratio all you like, but you cannot escape the absolute total. Entropy increases always. The second law does not negotiate. It does not bend for clever species. So a civilization faces a kind of squeeze play. To gather the energy and resources needed for interstellar expansion, it must dramatically increase its energy throughput. But increasing energy throughput increases the stress on whatever planetary ecosystem supports that civilization. And ecosystems are not infinitely resilient. They have tipping points. They have thresholds beyond which they do not gradually decline. They collapse fast, chaotically, like a bridge that holds and holds and holds and then suddenly does not. And once the ecosystem goes, the energy infrastructure that depends on it collapses too. You cannot run a fusion economy on a dead planet. You cannot build starships in a civilization that is scrambling to survive. Now, someone in the audience might think, what if they are out there and they are just being quiet? What if they are watching us and choosing not to make contact? I like that thought. It is a good red herring, and every good investigation needs one. But think carefully about what you are proposing. You are proposing that every single advanced civilization across the entire observable universe, civilizations that arose independently on different planets in different galaxies separated by millions of light years, has independently decided to adopt the exact same policy of silence. Every one of them, no exceptions, no rogue individual, no dissident faction, no bored teenager with access to a transmitter, no curious explorer has ever broken rank in billions of years. Think about our own species. We have never once in our entire history managed to keep a secret among even a few thousand people for more than a generation. And you are asking me to believe that billions of individuals across an entire alien civilization maintained perfect radio discipline for millions of years, and that every other civilization in the galaxy did the same thing, independently, without even knowing the others existed? That requires a level of universal coordination that I find extraordinarily difficult to believe. One species hiding, sure, two species maybe. But all of them? Across trillions of stars and billions of years? The math just does not support it. No, I think the simpler explanation is the more troubling one. The bottleneck is real, and it is made of physics. The window between able to destroy yourself and able to leave your star system is almost certainly very narrow, maybe only a few centuries wide. Think about what that means on a cosmic timeline. A civilization spends billions of years evolving, slowly climbing from single cells to complex organisms to creatures with brains large enough to wonder about the stars. 4 billion years on Earth, give or take. Then it spends a few thousand years building technology, agriculture, metallurgy, mathematics, engineering. Call it 10,000 years. And then in the span of maybe 200 or 300 years, it develops the ability to either reach the stars or annihilate itself. Let me put that in perspective. Compress the entire history of the Earth into a single 24-hour day. Life appears in the early morning hours. Complex animals do not show up until well past 9 in the evening. The entire history of human civilization, everything from the first campfires to nuclear weapons, occupies the last fraction of the last second before midnight. That is how thin the window is, and somewhere in that fraction of a second, a civilization has to learn to wield godlike energy without tripping over its own power. That window, that tiny sliver of time measured against billions of years, is where the test happens. And the question is not whether any one individual in that civilization is wise enough to be careful. The question is whether the entire collective system, billions of beings with competing interests, competing fears, competing ambitions, and access to increasingly powerful tools, can maintain enough coherence for long enough to thread the needle. Complex systems with powerful components are inherently fragile over long time horizons. You do not need everyone to fail, you only need the system to fail once. One catastrophic mistake out of billions of opportunities, across centuries of exposure to existential level technology. The statistics are not encouraging. So here is what I believe the evidence suggests, and I want to be honest about where the firm ground ends and the speculation begins. The great silence, the empty sky, the missing visitors. This is probably not a story about biology. It is probably not about intelligence or bad luck or cosmic rarity. It is a story about physics. The energy thresholds required for interstellar travel are so high that any civilization reaching for them is simultaneously reaching for the means of its own extinction. The capability and the danger are coupled. They emerge from the same equations, the same understanding of nature, the same mastery of matter and energy. You cannot have one without the other. That is not a political statement. It is a physical one. The gap between power and catastrophe may be so narrow that almost no civilization makes it through. The universe may be quietly littered with the remains of worlds that climbed 95% of the way there and then hit the wall. Not because they were foolish, because the passage was almost impossibly tight. And that is what makes this problem urgent, rather than merely interesting. We are in that passage right now. We have been in it for roughly 80 years, since the first nuclear detonation in the desert of New Mexico in 1945. We split the atom. We learned the trick. And in that same moment, we stepped into the corridor. We now have the power to destroy ourselves several times over. We do not yet have the power to leave. We are standing in the bottleneck. Right now, today, this conversation is happening inside the bottleneck. Physics cannot tell you what happens next. Physics just draws the walls and measures how narrow the corridor is. What we do inside that corridor is not a question any equation can answer. But the silence out there, that vast, patient silence stretching across billions of light years and billions of years of time, that should not make you feel lonely. It should wake you up. Because every civilization that ever looked up at its own night sky and wondered the same thing we are wondering right now, every single one of them faced this same passage. And the quiet that reaches us across 14 billion years of cosmic time might simply be the sound of all those civilizations that did not make it through. We are the latest ones to enter the corridor. Maybe we are the first who will walk out the other side. Or maybe the universe will be just as quiet after us as it was before. I would very much like to hear what you think. Does the physics win in the end, or do we find a way?